So first of all, thanks for the organizer to have invited me to make this talk. So my name is Yannig Goude. I'm also from EDF R&D. I'm a researcher in the same department than Xavier. And I will talk about semi-parametric models for load forecasting, which is a more technical talk than the one of Xavier, because I will focus on a particular statistical method. So, so the plan of my talk will be the following. First of all, I will try to motivate that approach in the electricity de France. I will present the semi-parametric models, I mean the statistical background, but in a very short way. I will focus on a big additive model, which is an innovation we made with Simon Wood for the University of Bath to apply this kind of model on electricity load for data. Then I will talk about application, and I have 3 examples of application. One on the French national demand. The other one will be an EDF portfolio, which is different from the national demand in France, as Xavier explained before. And the third point is forecasting at a local scale. I mean, I will present you forecasting electricity load on the distribution grid in France and also in US, because we tried this method for a competition which took place recently, organized by the IEEE Association. So historically, electricity load forecasting in France is a really is a main entry for centralized optimization process. So we have, as an enter of the production planning, the electricity load, which is then used for to optimize the production. And as EDF has a very big production park, a very small improvement in terms of electricity forecasting could reach very important profits for EDF. So this is very important. But now we have a new industrial context. As Xavier said, we have an open market since 2004 for industrial and big customers, and since 2007 for every residential customers. We have no, smart meters are coming, even if it's not sure. There is a project, Xavier talked about that before. We have 300,000 meters installed in 2 regions in France. And we have also different smart grids, experimentation. I mean, we have smart grid in Vendée, which is a region in France. Greenlist, which is an experimentation in Grenoble and Lyon. And Nice Grid, which is an experimentation of smart grids in the south of France. So this is a real project with physical innovations. So there is a need for local optimization due to the arrival of smart grids with demand-side management problems and maybe real-time communication with customers. Actually, the smart meters that could be installed in France are planned to receive and send information every night when the cost for telecommunication is not high. Okay. We have also to deal with development of distributed production units, and this is a very important topic due to the increase of wind and solar energy. So the impact on load forecasting of such new context. For open market, we have to develop adaptive method, robust to loss and gains of customers. For the arrival of smart meters, we have to deal with big data analysis, online data flow treatment. We have to develop new statistical model to integrate this large and benefit amount of data. To deal with smart grid, we have to forecast at the local scales, as we would probably have to optimize locally the production plan. So we need electricity forecast at that scale. For real-time management, demand response and new electricity tariff will entail changes in the way we build statistical model. Maybe we have to think about demand control optimization problem, something like that. And for distributed production units, we need to do probabilistic forecasts. So now, semi-parametric additive models, briefly, we will consider additive models. I mean, the electricity consumption, which is denoted the yi here, could be decomposed in a sum of different effects. Some of them are linear, which is a classic regression model. Some of them could be non-linear. In that case, we will consider that these effects are smooth. For example, you could see x1 as a temperature effect, F2 as the effect of calendar variables, and F3 tariff options or something like that. So to estimate such a model, we have to solve the following optimization problems. So we minimize the quadratic error plus a constraint, which is which depends on a regularity indicator of the functional we want to estimate, which is the integration of the second derivative of the function here, just because we want to use a cubic regression spline estimator. So this is a very well-known statistical method introduced by Asti and Tipsharani in the 80s. And recently, we refer to the work of Simon Wood in a book he wrote in 2006 with a quite new algorithm to make the estimations. So we use a basis expansion in a spline basis to estimate these functions. And doing that, we can go back to a classic regression problem, and we have a lot of techniques to solve it. The only unknowns are the position and the number of nuts for the spline basis, which is quite a complicated problem. But we go over that problem taking a large number of nodes on a partition, and then we proceed to regularization of the functions with a quadratic penalty, as in the rich regression methods. So we solve this simple rich regression problem, which is a well-known problem, and we have an estimate of the functions, of the smooth functions. But we have to deal with how to choose the penalization parameter, lambda. To do that, we use a well-known criteria, which is the generalized cross-validation criteria introduced by Craven and Waba at the end of the 70s. The advantages of such a criteria is that lambda could be obtained by numerical optimization, and so it's quite fast. And it will work on big data problems. And for the big data problems, we have also the property that this criteria is invariant doing a useful transformation of the data, as you will see. So the software we use is the R software, and the package is the MGCV package of Simon. For the big data, we use classical algebra transformation of the data. We use the clear decomposition of the data. So I will go fast on that presentation, but we have a paper explaining that. And what is interesting is that when you use the Courier transform of the data, you can invert your matrix, your big matrix by blocks, and so you can decompose a big problem in a lot of small problems to do your mathematical optimization. We use also that techniques to update parameters of complicated semi-parametric models when we have new data arriving online. This is very useful. So now I will talk about the applications. Well, the first one is the French electricity demand. This is, the simplest one. So as Xavier explained, we have different patterns in the electricity load, and we have the French electricity demand is highly sensitive to meteorological conditions because of electrical heating and cooling. We have to deal with three seasonality, the yearly, weekly, and daily patterns. The yearly pattern is mostly explained because of lightning, and economic cycles during the year. The weekly pattern is simply the way of life of people who works on weekdays and stop working on weekends. And the daily pattern also could be explained that way. And there is also a third part, which are the tariff effects, because in France we have peak and off-peak tariffs, and that have an important impact on the electricity consumption. And we have special contracts with big industrials that could be activated on peak days. So this is the consumption from 2002 to 2009. So you can see there is a trend in the consumption, in the French electrical consumption, simply due to the increase of the number of people in France. Okay, and maybe also we have more and more electricity consuming usage. We have a yearly pattern. So consumption is higher on winter and lower on summer, and we have a big holidays effect in August here. And as Xavier said, a few special days during the year. We have a weekly pattern. This is 1 month of data, so you can clearly see each weekend's decrease of the load. And we have also daily patterns. What is interesting here is to see the day and night effect, but also the effect of special tariff, because we have off-peak tariff between 12 and 2 in the afternoon each day, and at the end of the day, around 10 o'clock, there is an automatization of warming system for water. Okay. So this is the tariff effect also. And special days, here you have a day with a normal tariff and a day with special tariff in dash line. So you can see we can stop a lot of big customers during winter when the consumption is high. Just saying, okay, if you have a contract, you pay less electricity, but tomorrow if you consume, you will pay 50 more than the normal price, 50 times more. So it works. And here we have an example of bank holidays. This is temperature relationship. The relationship between temperature and load, as Xavier explained you before. I will go fast. And this is the model we propose for electricity consumption. Yeah, it doesn't look very beautiful, but you can see each effect of the consumption in the equation. The first line is the mean level of electricity load for each type of day, plus the shape of the day, which is a nonlinear function in function of the hour of the day. Then you have a second line is the temperature and lag temperature effect to deal with the inertia in the buildings. We have also introduced the yearly cycles using cyclic splines. This is the equivalent of Fourier transform of Xavier before. And we have a trend and also a lag load effect, just to deal with small change in the data along the time. We have around 100,000 observations to deal with here, because this is half-hourly observation during 5 years. And the number of the estimated degrees of freedom of this model is about 800 parameters. So just to give you an idea of the complexity of the model. That's why we talk about big data problems. Actually, we don't have so many lines, but a lot of columns in the matrix. So this is an example of the estimated daily shapes. So you can see we found the Friday effect, the Sunday, Saturday, etc. This is a temperature effect in function of the hour of the day. And this is the result of our model. So we have about 1.5 errors on this data. Yeah, as given in this table. So I have to go fast, maybe. So the other application is on EDF customer portfolio. So EDF was the only provider. We can lose and gain customers. So there is a non-stationarity to deal with. To do that, we use adaptive semi-parametric models. We use the previous models, but adapted in an online fashion. So we use Kalman equations to estimate the different parameters of the model, and doing that we could introduce a forgetting factor to forget the data which are too old in the past. And doing that, we could deal with loss and gain of customer. This result could be found in a paper. I will give you the list of the different papers at the end of the talk. So we compare a lot of different online rules and say, okay, it's okay. We can have something like 1.6% error on the EDF portfolio with that. Another application is on US data from the JEFCOM competition. So this is a screenshot from the competition organized by IEEE. So we got data from US. These data, I think, are still available on the website of Kaggle. So if you want to test it, there is also wind forecasting, but we didn't participate. So the data set was we were given with 20 electricity substation data recorded only on the US grid, but at unknown locations in US. Okay, and we have also 11 temperature series at also unknown locations. And the objective of the competition was to forecast the next week of data, and also to backcast 8 weeks in the past. So we have to reconstruct the electricity load, just knowing the temperature. So these are the data. So you can see very different curves and very special consumption on the right. Mainly due to industrial processes or something like that. We don't know exactly. And the EDF team's work is presented also in a paper that will appear, I think, in the next month. The idea was to decompose the electricity load in 3 parts: one for the long-term load, one for the middle-term load, and one for short-term load. Okay. The middle-term load. In the middle-term load, we use GAM models. For the long-term one, we use simple GAM models to focus the trend of the load on monthly data. And for the short-term correction, we use the random forest technique to capture local structure of the load. We obtain that kind of estimation effect. Which is interesting is that on the left you can see the temperature effect on one substation in US, and you can see that the cooling effect is far more important than in France. And the model can see it automatically, without any. Actually, to be honest, we didn't spend too much time to refine the model and to correct the data. It's quite automatic. And we finish first on the public leaderboard, but 4 at the end, because there was a public leaderboard available online, but maybe we overfit a little bit the public leaderboard. The explanation for the 4th position is that I think we missed the forecast of the last week of data, because we didn't have the temperature data, so we also had to make a forecast of the temperature, and we don't know that. Actually, that's not our specialty. So we had a lot of problems with that. The last application is on forecasting on the French distribution grid. So we have to forecast here for ERDF, which is the French distribution network manager. We have to forecast 2,200 substations over the French territory. You can see it on the map on the left. recorded at 10-minute frequency. So it's a lot of data, 2,200 time series at 10-minute frequency. For me, maybe not for everybody, but for me it's a lot of data. And very, very different data that, as you can see on the right, you can have a substation with a lot of residential, other with industrials, and mixed of everything. So we have fitted GAM models also automatically on this data. It worked quite well. You can see here different effect estimates. So this graph is the temperature effect over the day for one substation. We can recover a specificity of residential consumption in France because of off-peak and peak tariff. A lot of people warm their home in the night because the price is lower, and you can see it on the graph. And you can see the effect of off-peak and peak tariff on the left with spikes on the estimation curve. So the performances we obtain are presented here. So we have a short-term model, which is denoted CT here. This model provides day-ahead forecast. We have a middle-term model to provide forecast for 1 year ahead. And we compare it to naive forecaster, which is to forecast tomorrow, I just use last day consumption, and to forecast next year, the last year consumption, which is this naive forecast. And this one is just the consumption of last week. So actually, we did, I think, 2 times more, 2 times better than the naive forecaster. And for the short-term forecast, the median MAPE is about 5%. So that means that 50% of the substation are forecast 1 day ahead with a 5% precision, which is not so bad. And for year ahead, it's about 8%. So it's quite okay. So conclusion, so semi-parametric models, they achieve a good trade-off between calculation times and performances for classic data at an aggregated levels. And we could proceed to parallel estimation of 2,200 models over 6 years of 10 minutes data. Actually, it took about 1 day on a quite big computer, but with 8 CPUs. So it's really, I think it's really quick, and it could be easily applied to various electricity data sets. But I think we could improve in different ways for online updates to be more reactive to changes, and also to improve the stability and maybe the identifiability of the estimators in that field. We also work on automatic model selection with GAM models. I mean, just select some covariates or not in that kind of equations. And also variable coefficient models to exploit the common feature between different time series. So thanks. And here are some few papers about that.
Right, do you have any questions? Stan.
You mentioned special pricing for some large customers
Yes.
and on certain days.
Yes.
And the number 50 occurred there.
Yeah.
I couldn't work out whether it's 50% or a factor of 50.
Yeah, 50 more. The price is really big. On those
Huge.
Huge.
Yes.
Yeah.
Okay. It's rather like, in this country, National Grid have a triad system where they retrospectively charge you huge amounts of money if you happen to be so foolish as not to guess the day in which consumption was going to be particularly high.
Yeah.
This is very effective.
It works. works over the cold days.
Yeah, it's because I think, on very, very peak days, we don't have any production plan to provide the consumption. So. And it could happen, I think, 20 times a year, 20 days into a year. We can decide from one day to tomorrow if the tariff will be on or off.
But the customers have advance notice.
Will it be what?
The customers know in advance.
Yeah, just one day in advance.
Is that part of the contract that they stipulate how many days a year they can be shed?
20 days a year.
It is that's part of the contract. Yeah. It's interesting. But there could be effects at the end of the year. You know?
This is like a game between the
Yeah.
provider and customer. Yeah.
You know, I had a question because you just say your test cases are getting bigger and bigger, and actually I think one of the potential challenge is are all the mathematical tools and theory we have today able to just scale up and be available for all these big data that are coming up? You mentioned some. I mean, there's dynamic factor models. There's this factorization. There's different ideas.
Mm.
But is this going to be good enough and practical enough when you have all these smart meters everywhere, data every 5 seconds?
Okay.
I don't know.
I
What do you
think
think?
we have that in mind when we did the test for the substation on the grid. And what is interesting with the model we developed is that you can parallelize the calculations. So if you have, 10,000 or 100,000, yeah, you just buy more computers, so it's okay. But we made a few tests with the simulation platform Xavier mentioned before, and we work with IBM to use highly parallelized platforms to make those kind of calculation on millions of time series, and wow, it works quite well. Yeah, actually, surprisingly, not on millions but on 100,000, which is quite okay because you don't want to forecast each curve for each individual customer. To really make some small aggregations of 100 customers, and that's okay. We can do that.
So the big player would be IBM, not Google?
No. I mentioned that just because we have a research collaboration with them, but I don't know what Google do.
A detailed question, why do you call your model semi-parametric?
Because we have nonlinear effects that could be considered as functions.
At the end, you make it completely
Yeah.
parametric.
Yeah, but that's the vocabulary in statistics. When we call that semi-parametric models because it's parametric, but on basis of functions.
Semi-parametric would have an infinite space somewhere,
Yeah, right.
which you don't.
Yeah, we have actually.
Yeah.
Is temperature the only weather variable that you consider?
No. I like to show the temperature effect because it's quite simple to understand. But we have also other meteorological covariates like the cloud cover. We could consider also the wind for some region in France. It could be interesting. Not for now because it's a kind of we don't have a contract with a data provider for that kind of data. But I think for local forecasting it would be useful to consider rain, wind, other meteorological covariates. Also, we have a lot of calendar variables and tariff variables.
Some papers hinted at the fact that the renewable variability would be much larger than the loads forecasted area.
Yeah.
So, in some sense, what's the value of, so I'm being provocative, what's the value of refining the forecast of the loads when people will start installing PV roofs and windmills around that will introduce a lot of variability in the distribution networks as well?
Actually, as to estimate the variability in electricity production or demand, we use for now we use electricity consumption models, and we put a methodological scenario as an entry, and that just estimates the distribution of the load. So if you make a small error in your electricity consumption models, then you will obtain very large intervals, and so maybe there is an interest to improve if the variability is becoming more and more important. I don't know if it's this is one part of the answer. The other point is that this model could modelize in one way. You could introduce production in the model also. It could be a way to optimize the equilibrium, to have a single model to do all that kind of stuff. But yes, you're quite right.
Yes.
Sorry, this might be a very obvious question, maybe I missed it, but so where does the temperature and the meteorological data come from this? Is it that you're taking a perfect forecast of the meteorology and then trying to get to the load forecasting from that, or is there a forecast of the meteorological properties as well?
Okay, my topic is on electricity demand models.
Yeah.
So I don't want to embed the temperature forecast error in my experiments. I want to see if I have a good forecast, what will be my error. Okay? So this is real temperature data. I'm not forecast temperature data. Actually, when we want for a question of forecast, we did some experiments with forecast temperature. But this is we suppose that this is uncorrelated. The temperature forecasts are uncorrelated with demand forecast.
Okay. Can I make just a follow-up thought from that then? Is if you're including other meteorological variables as potential predictors in your model. Now, meteorological forecasts are better at some properties than others. So it might change the power of your model when used in the genuine forecast mode. So windy, let's say, forecast less accurately than temperature. So it might change change the relative quality of the models.
That's right.
Compared to each other. So
that's right. Temperature is quite well-known methodological variables. For wind, it's more difficult. Yeah, right. You're right.
But I mean, the actual meteorological forecast of it is more difficult as well as perhaps the linking to the.
Yeah.
Right. Thank you.
The load shape for a given day, does that change according to the type of weather you've got, or does it?
Type of weather? Yeah. Actually, for example, let me see. This is the mean of the load for the overall period. But in winter, the peak at the end of the day is more important than the peak at noon. Okay, and it changes along the year, depending on the electrical heating mostly. So when you heard about
that's a seasonal effect, isn't it?
yeah, yes.
Is there a day-to-day weather variability in the load shape?
It could happen. Mostly, for example, if you have one day without any cloud and tomorrow a lot of clouds, then you will have probably a lightning effect in the afternoon, which is totally different between 2 days. You can also have an impact of temperature variability from one day to another. If you have a big derivative in the temperature, it could have a big impact on the electricity forecast error. Yeah, it's difficult to forecast, something like that. Yeah.
Yes.
Yes, so in terms of judging the error in your forecasts, are they just based on a least squared error?
Yeah.
Any thought into whether that's the best error metric? Because presumably some parts of the day it's more important to get it accurate than another part of the day.
Actually, we choose to give the same weight to positive or negative errors on the load, but for example, you could use other loss functions. This is not presented in that talk, but we try different experiments, like reweighting the data for the peaks or for special cold winter, etc. and just obtain different forecasters. This is research work because what is difficult after that is to combine the different forecasts to produce a good forecast. And the other point is that you could think about optimizing your model conditional to electricity prices, for example, and use that prices to have weights on your data. And, but doing that, you make something, I think, not understandable for the Commission regulation of energy, because you change the future of the load according to what you want to observe, and this is not very clear to do that. We try to be independent from the prices. Thank you.
Right, well, thank you very much indeed.